So I'm Daniele Micciancio. I'm a professor of computer science at UC San Diego. But right now we are at UC Berkeley, specifically the Samus Institute, where I'm spending 3 months as a long-term visitor for a special summer program on cryptography. And this actually a 10-year, so the title of the program is Cryptography 10 years later. So we had a similar program here 10 years ago in 2015. And we organized this program inviting some of the researchers that were already back then. And of course, there are many new people, and a lot of things changed. So 10 years ago, I was one of the organizers of the program, and specifically I organized with Chris Spikert a special workshop on the mathematics of cryptography. And one of the big topics, in fact, the main topic of that workshop was certainly lattice-based cryptography. And very interestingly, now, 10 years later, lattice cryptography, which is the main player in the area of post-quantum cryptography these days, is not even a special topic on its own. We don't even have it has become mainstream by now, so we don't even have a workshop dedicated to that. But of course, it often comes up in the workshops. Other activities organized during this program at Simons.
Nice. And in San Diego, you are in the Department of Computer Science and Math, but the cryptography part is within.
I'm actually in the computer science department, not in math. And I've always been a computer scientist. By training, I got a degree in computer science, a doctorate in computer science, but I always liked math. Sometimes people think my work is very mathematical. I work on the mathematical aspects of cryptography, and often people think that I come from mathematics, but no, I'm a friend of mathematics. That's what I call myself. And so mathematics, of course, plays a very important role in cryptography. Cryptography is based on problems which are hard to solve. In some sense, cryptography is the happy side of computational hardness. So usually when there's a problem that you cannot solve, there's no good news. You want to solve it, you cannot. You do not have efficient solutions for it. And that's an obstacle. So in cryptography, you try to exploit this hardness to do something useful, to build systems which are hard to break, and use that to protect information, to protect transactions. And mathematics is a very good source of hard problems. I mean, the type of harness that you need in cryptography is a very special type of harness. You need something which is very, very hard.
Yeah, and the history of cryptography is also long, and we went through maybe symmetric encryption, and then we went to use the asymmetric encryption, the public key, which actually is not that much old. It's like from the 1970s, and especially the wide use of it. If you think about PGP, that was actually more 80s or 90s even. And as an expert in this field, I was wondering, so encryption is being broken multiple times, and now we have been relying on this new form of encryption, the RSA, pretty much for this long. And I wouldn't say it was naive, because of course it was very helpful for many, many decades. But what do you think? Now we reach the point when we really need to move on, and everything we had for this part of history of cryptography is part of the past?
So this complex question. I mean, it's a simple question, but I mean, the simple answer is not quite right. So let me explain. So RSA, or more generally, cryptography based on problems from number theory, like factoring. There is a similar problem called the discrete logarithm, which is close to the type of problems that were suggested in the 70s, as when the idea of public key cryptography first came up. So first of all, even leaving quantum computing aside, So we have much better algorithms to solve those problems now on regular classical computers than people had back then. I was barely born, that's why I'm saying people. And there's been much progress simply on the algorithmic side. And of course, the fact that the problem was being used for cryptography was a good motivation for computer scientists and mathematicians to look into the problem, trying to find better solutions to these problems. So quantum computing just added one more line of attack to those problems. We were already using keys. So keys are numbers that are hard to factor. And of course, we know how to factor numbers. 15 is 3 times 5. And you can even factor it using a quantum computers experimentally. This was done. They were able to build quantum computers powerful enough to do that. Now, if people find better algorithms, then you need to use larger numbers to fence against those attacks. What changed with quantum computing is that in the mid-90s, people working in the area, and Peter Shor specifically, came up with an algorithm to factor numbers, which is theoretically efficient. It's something that, at least in theory, you cannot avoid just using larger keys. I mean, using larger keys, you will have to invest more time to break it, but not by a large, huge margin. So it will cost more, but it is still feasible. And of course, we don't have quantum computers big enough, large-scale quantum computers that can run that algorithm yet. But the theoretical possibility of building that was already clear the moment that he came up with this algorithm. So interestingly, around at the same time, there was a major development in the mathematics of cryptography. This other researcher, Miki et I, at the time at IBM nearby here in the San Jose campus, Almaden campus, he came up with a mathematical proof showing that lattice problems are in a sense very good for cryptography. Now, we have plenty of hard problems in mathematics, but in cryptography, you need problems which are hard to break on the average. So it's not enough that you don't have an algorithm that always solves the problem. That's typically what you need in applications. You need an application that always works. You don't want something that sometimes works, sometimes doesn't. That wouldn't be reliable. But in cryptography, you want to make sure that your cryptographic function cannot be broken most of the times. So when you pick your key at random, it's not enough to know that there is some key which is hard to break. Right. You want to know that your randomly chosen key is going to be hard to break with very high probability. So you need a mixture of hardness and also structure that shows you that you have this type of refined hardness. So what I managed to show, this was 1996, I believe, in mid-90s, so around the same time as Shor's discovery, he showed that certain problems on these mathematical objects called lattices, if you can break them, if you can solve those problems on average, even with very small probability, then you can solve lattice problems in the worst case. You have a general purpose algorithm that will find a solution for every single instance of not exactly the same, but closely related lattice problems that the mathematicians have been interested in for centuries. Some of these problems had been used in mathematics. Lattices are high-dimensional objects. So the basic objects are point in n-dimensional space for a pretty large n in cryptography, a few hundreds. For two-dimensional lattices, already Gauss had found an efficient algorithm to solve lattice problems, but it was specific to the two-dimensional case. And scaling that algorithm to a high dimension seems to be exponential time in the dimension of the lattice. So just adding, every time you add one more coordinate, let's say that the running time of the algorithm doubles. In fact, at the time it was growing even slower than that. Finding algorithm where adding one dimension only doubles the running time, that's something that was achieved only in this millennium, 2000 something. So this pointed to lattices as a very good source of harness, specifically for cryptography. Now, you asked about RSA. RSA is a well-tested problem. We have better algorithms, but a lot of people looked at it. So we don't expect major changes from one day to the next. A substantially faster algorithm to break RSA today would be quite unexpected. It could happen, as it happened a few times in the past. Perhaps people will find a classical algorithm that solves factoring efficiently and showing that, you don't even need quantum computers to do that. But those would be major breakthroughs in mathematics. And these things do happen. I mean, don't be mistaken. There is the probability of this happening is non-zero, but it is something that people consider unlikely.
Still now, yeah, but I'm so glad he's saying that, because most of the people would not admit that. They would say, no, this is like math, this is unbreakable forever, but it's still an assumption after all, because we didn't get there yet. I mean, maybe it takes 100 years, maybe it takes a week, we don't know. But definitely is something that is math that we didn't discover yet, right?
So the way cryptographers look at this is a win-win, which means, we want to solve those problems. Mathematicians are interested in the problems. If cryptography gets broken, well, we're going to be happy anyway. Okay, so I mean, cryptography and security is not the only issue here. So having problems that are interesting for other reasons is a way to attract attention, to have people look at it. And that's true. In large part, our confidence in the security of cryptography and even the post-quantum security of lattice-based cryptography is based on the fact that we tried to solve these problems for a very long time. So lattice problems, so there was a good reason to think of them as good cryptographic objects for mathematics. But typically, when you take a mathematical problem, you don't know how to solve it. So it seems hard. But when you use it for cryptography, you need to come up with a specific way to use it. How do you choose your your keys that you're going to keep secret? How do you use the key to encrypt messages? That also has to be a randomized process. So randomness has a fundamental role in cryptography. And whether a problem is easy or hard, when you look at the randomized complexity of the problem, that depends on the distribution. How are you choosing things at random? For example, if you give me a random number between 1 and 1 million, I'm pretty sure I can factor it. If half of the times is even, I can tell you, oh, that's 2 times 1/2 that, okay? Maybe a multiple of 3. So finding the correct way to pick problem instances at random so that they are hard to solve with the distribution, this has always been the trickiest part of coming up with good cryptographic functions. So what was remarkable about this discovery of ITI is that it was telling you mathematically what is the correct way to use lattices in cryptography, how to choose them at random. And that's true. Perhaps they will come up with an algorithm that solves lattice problems, and I mean, some of them are NP hard, so finding solutions to those it's still possible, it's still an unproved assumption that there is no efficient algorithm, but that would be quite a major, way bigger than quantum computing. So showing that NP hard problems can be solved efficiently would mean that cryptography does not exist. It's not that we don't know how to do it. There's just no way to do it. It just does not exist.
Interesting.
It's something that we invented. It's science fiction, but it's not reality. And it's not that we didn't discover it yet. It cannot possibly exist. It is contradictory with the laws of nature, as long as you think of computation as a natural phenomenon, which many people in computer science think.
That's why we call this project post-encryption, not post-quantum encryption.
Exactly.
It's kind of, it's a working title, but we're also exploring that direction.
Exactly. It's really the questions that should be asked right now. It's the full set and includes these couple of questions such as, and what happens if also we realize something? This is the good discussion. In selecting the keys and the advantages there for Lattice is very clear. It's kind of it's hard to solve. You have to make sure it's also not too hard to set up, because the asymmetry is what you want. It should be choose your keys correctly, and then it's a one-way street, so to speak, and hard to come back this way. But if it's too hard to go that way, then you also don't have the asymmetry you're looking for. Is that fair to say?
Yeah. No, but asymmetry is fundamental here.
Yeah.
And even for much simpler problems than encryption. So what I discovered back then was how to build a one-way function, a function which is easy to compute. In fact, it was very, very easy to compute, no matter how you choose the key. Okay, so for every key, it's very easy to compute in the forward direction, but computing it backward seemed incredibly hard. Yeah. And there's a huge gap. So it's not that you need there's a very big margin between the two things. So one is theoretically, it's called the polynomial time. In fact, for lattices at the time, it was quadratic time. It was a time similar or cubic time, something similar to the operation of multiplying a matrix by a vector, simple operation. While inverting the function is exponential time. That's the best that we know. Now, in practice, quadratic time is not quite enough to be truly practical. So after IT's discovery, there were two main open problems for lattice cryptography to become useful. One was how to develop more interesting applications that simple one-way function. So who wants a function that can be computed forward but not backward? It's not an application yet. It is complexity theory. It is a cryptographic object because it exhibits this type of refined high probability harness, but is not by itself a useful application. And so there's been research in developing more interesting application. And the other angle that needed to be tackled was efficiency. Now, quadratic time is theoretically good. It's something you can use if you don't have any other solution. But you want, if you didn't have any other solution, you would use it in practice. It would be usable. But typically in practice, you want something that is much, much faster than that. And that's where, there were two major developments that made cryptography, lattice-based cryptography, what it is today. One was to look at structured lattices. Rather than looking at arbitrary matrices, you can take matrices where, I'm oversimplifying things here, where every vector is a rotation of the previous one. So you can represent the matrix in a compact way. I just give you one column, and then you take all the rotations, and you get an n by n matrix. So this is something that in some form was already done by this crypto system called NTRU, that was suggested also around the same time as in the mid-90s. But there was no good theoretical understanding of that system. And in the early 2000s, so I managed to show an efficient version of ITI's discoveries, so that if you take these structural lattices, you can prove the same type of refined hardness that says, if you can break this with even very, very tiny probability, then you can break it for every matrix has this type of structure. And that made lattice cryptography much, much more attractive in practice from an efficiency point of view. And so using that, you can already build many interesting applications. So they were not built right away because there were not many people working in lattice cryptography. I mean, at the time, I was one of the 4 people working on it. Okay. And but you could build digital signatures, you could build collision-resistant hash functions. One of the applications that is really getting a lot of attention these days is proof systems. How to come up with the proofs showing that something is true, but the proof has to be very, very short and easy to check. So using lattices and using cryptographic functions that can already build out of this iTice function or the more efficient version that we suggested and built using structural lattices, you can build succinct proofs. I mean, there are also other methods to do it, but there would be a post-quantum, quantum-resistant way to do it. And these are very interesting cryptographic objects. Mathematically, we think of proofs as something that it is written down and it is either correct or incorrect. If it is incorrect, of course, it's not worth anything. But if you check all the steps of the proof and all the steps are valid, then you know what it means. Okay. Now, in computer science and in cryptography, we have this thing called computationally sound proofs, which are proofs which in principle, even if you check it and the check passes, perhaps the statement that you proved is still false. So you're proving a false statement. But you can show that finding proofs of false statements is cryptographically hard. So even if there are proofs of false statements, they will not occur in practice. The only way to find those proofs is to solve problems which we think are not solvable with reasonable computational effort. So if somebody comes up with a proof and shows it to you and you check it, then you can be confident that, the statement must be true. One of the applications that has been bringing a lot of attention to these succinct proofs is blockchains and cryptocurrencies. When you wanted to perform some computation off-chain, and then put a short proof in the blockchain, and that allows to offload the computation.
Oh, right.
But something I wanted to mention, I said that there are 2 things. One was efficiency, using structural lattices, and that's how we do cryptography, lattice-based cryptography these days. The other one was building more applications, and another fundamental step was a variant of this problem, the problem, iTice problem that was called the SIS problem, the short integer solution problem. Okay. And in the 2000, around 2004, 2005, Oded Regev came up with a variant. I mean, it's something that today we understand as a variant of that problem. And when he came up with it looked very different when it was first suggested. And it is an easier version. So in some sense, it is less secure than SIS. It's called the learning with error problem. And it is, in some technical sense, easier problem. So it is a stronger assumption to assume that it's hard to break, but it opens a much broader range of applications, including public key encryption, which is something that could already be done before using lattices, but in a more contrived way. So LWE, as people call it, learning with errors, allows to do public key encryption. And something that was discovered a few years later, in 2009, was that using this type of cryptographic constructions, you can even build encryption schemes that allow to perform computations on encrypted data without knowing the decryption key, without ever decrypting things. And the first solution to this problem was discovered by Craig Gentry in 2009. So at the time, people thought that, perhaps this is impossible. How can you possibly compute on encrypted data without knowing what you are computing on? And he came up with a brilliant idea showing that, yes, there is a way to do it using lattices. The way he was using lattices was not quite the standard way we use them now, or even back then what seemed to be the best way to use lattices. And better ways to do it using standard lattice problems were discovered within a few years. But in some sense, his discovery was the turning point that convinced people that the problem was solvable at all. Before, people were not quite sure it could be solved. So the moment you know that the problem can be solved, a lot of people start looking at it.
Yeah.
And that was perhaps even more than the post-quantum angle. That's what brought a lot of attention to lattice-based cryptography. And since then, the field has been booming, exploding.
Yeah.
When we had this special program here at the Simons Institute on lattice cryptography and cryptography more general, but with a special workshop on this topic, and many lattice cryptographers coming here. So at the time, lattice cryptography 10 years ago was already well established, with a lot of people that wanted to do it. People were considering starting companies to build commercial products, and there was a lot of theoretical and practical interest.
It was already taking off.
I want to have some question that moves us away from the most more technical parts and these lattice things. You were interested in talking about the ethics of quantum, or at least the freedom, if I understood correctly, because we were just chatting, like more the freedom of breaking encryption and how it is inevitable, everything that will come with it. And it's also, I guess, it's also about the freedom of science, the freedom of scientists, whatever it takes, whatever are the consequences, or what are your thoughts about this?
Yeah, I'm not sure I would frame it as an ethic question of should cryptographers try to break cryptographic functions? And is it ethical? I mean, that's the only way we can gain confidence that those things are secure. And if they can be broken, better know that they can be broken. So in some sense, you want to do that. Of course, if you find an attack to a cryptographic function that is being used, it is ethical to go through a process called a disclosure process. First, you wanted to notify the companies that are using it, the people that are using it, suggest a possible way to fix the problem. And that's called ethical disclosure. And usually before announcing the result publicly, you go through this process, and it's very, very common. I mean, this is the standard within the research community. So in some sense, even from an ethical point of view, trying to break things is what we should be doing. That's the only way. And I mean, even scientists doing that, that's the ethical thing to do. You don't want to leave that to the unethical people.
Absolutely. I think the point is the after things are broken, what happens also to the scientists, but also to society potentially, or business. I mean, the disclosure moment, how long should it take? Because if something is so disruptive, what do you think?
So building a quantum computer, this of course is a different, big question.
Yeah, we're
General
talking
disruption.
For the day-to-day type of, so this happens not every day, but it's very, very common. This happens every year. There are multiple cases of products that are discovered to be vulnerable. And I mean, typically, you know how to fix things. It's not that you know how to avoid the attack. There is a cost in implementing the fix. And often, unless there is some kind of, I don't want to call it threat, but if nobody were to look at the security of products, things would be way worse. So the fact that attacks are discovered, and once they are discovered, if I discover an attack, I don't do cryptanalysis, it's not what I do primarily. But if I discover an attack to a system, many other people may discover it. It's not that I'm the only person that can do things. So I don't know what is the standard time frame, but typically, so there is some kind of process that one goes through, ask to the interested parties how much time do you need to fix it, how much time do you want before we announce the result publicly, before it could be it could be
Disruptive, very disruptive.
used, and typically, I mean, everybody's concerned about this. Now, quantum computer is different. Building quantum computers, so you can think of quantum computers as the ultimate quantum physics experiment. I mean, we have plenty of experiments already that somehow tell us that quantum physics is the description of reality. And so we know that quantum physics works, and there are many applications based on the principles of quantum physics. But quantum computer is something that would represent, you can think of it an experiment about quantum physics to check if the principle of quantum physics work, it can be made to work at a scale which is much, much larger than any experiment that has been done in physics in the past. So think of it as a way to understand the universe.
That's a cool way to say it, and you're right. It will be the ultimate check because the math should add up in ways that can actually be built upon as opposed to just measured. That's cool. Yeah.
Yeah. Do you have a question?
No, I just wanted to comment that that's a great way to think about there's a bigger experiment behind quantum computing than just can we make applications from it.
Well, that for sure.
Yeah.
I mean, if you look at this historically in the past, all the debates about the heliocentric theory or geocentric theory, is it one going around the other or not?
Yeah.
Everybody knew. In fact, it was already known before, but the fact that you could do better and more experiments showing that I mean, that's the truth. It's undeniable. And there were some interested parties that perhaps wanted to present a different story, didn't go along with their narrative, and you cannot stop the progress of science, and understanding the universe we live in is something that is good. I mean, you cannot. Ignorance is not the solution to security, as well it is not the solution to many other problems in the world.
Is there something that you personally are waiting to see implemented as an indicator? This will green light, this is likely to work, or oh no? Is there some in particular computational result or implementation of quantum computing that will give you either a good feeling about what's known, or will tell you there's something else to look at?
So actually, I don't think I'm the best person for that, because that's quantum computing, and that's not really my expertise. Lattice post-quantum cryptography, lattice-based cryptography, and
Sure.
But you can get better. Umesh probably is.
Maybe it's about also the implementation of lattice cryptography. How long and how, and if you think it's 100% secure, or
there is. We don't have 100% anything. So everything it's our best understanding of cryptography in the world around us, and the pre-quantum cryptography is not any different. So even without quantum computers, our reliance on factoring-based or elliptic curve-based cryptography is based on our current understanding of mathematics. Now, we already have good solutions for post-quantum cryptography. So lattice cryptography has been truly investigated for 30 years now, and we feel pretty confident about it. Something that people are considering doing is to combine it with the traditional cryptography. So why switch if you can use both of them in a way that as long as one of the two is secure, we are safe? Because historically, if quantum computers don't get built, we have a good understanding of the security you get from traditional cryptography. So let's add the post-quantum to it, which is our best answer to the threat of a quantum computing, of a quantum computer. And these things are already implemented. There are actual protocols. So post-quantum cryptography, lattice-based post-quantum cryptography, in fact, the type that has been recently standardized, picked as a standard by NIST, is already implemented, I think, in TLS, the protocol used to secure web transactions. It is implemented in OpenSSH, which is another commonly used protocol for securing a point-to-point connection and the construction of a VPN, virtual private networks. So we already have implementations. In fact, we already had the implementations already a long time ago. What we have now are people interested in using it. So
you think that if the public key cryptography system we have in place today would be broken, let's say tomorrow or next week, a lot of things will be already there for that moment? I mean, they will still function, like the financial system, like very key infrastructures too, because you are saying these post-quantum cryptography systems are already in there. They're already used in this critical communication. So
the science is there.
the science
is
there.
there.
But not the implementation.
The engineering, the implementation also. These systems have been implemented for a very long time. We know we have very efficient methods to implement them. We know how to do it. We already even have chips, hardware to accelerate that type of cryptography. Of course, all of this so far has been done more in the context of building prototype systems to show that you can do it and how well you can do it. Now, deploying something, so once you have a solution which is ready to use, actually changing and getting people and company to switch from one system to another one, there's a big, it's almost a social engineering process. So that's a totally different story.
It will take years.
People talk about, not just for this, so any change of this type in industry, the time scale that you should consider is 10 years. If you have something that is ready to use, if you think that 10 years from now we may have that type of quantum computers, we need to start working now on replacing, and that's why there is a lot of interest now in switching to post-quantum cryptography, even if a quantum computer capable of breaking cryptography is not quite yet around the corner.